Let's talk about network covalent solids. Carbon is a very important one. Elemental carbon exists in several different forms. These are called allotropes. The two you might be familiar with are graphite and diamonds. In graphite, we have two-dimensional sheets of carbon atoms that are bonded together. The individual sheets are just held together by dispersion forces, and so these sheets will slide relative to each other, and that's why graphite is slippery. So if you're writing with a pencil, your pencil lead has no lead in it, it's graphite. And the reason it works nicely is because as you push it across the paper, the layers of graphite slide away from each other and stay behind. Graphite's also useful as a lubricant because it's slippery. It's a good electrical conductor because there's an extended pi bonding network in these sheets, and so the electrons can move through that pi bonding network. If you take graphite and put it under very high pressure, the carbon atoms will rearrange and form a diamond. Graphite has a density of 2.2 grams per cubic centimeter. Diamond has a density of 3.5. It's more dense. Diamonds are naturally formed deep underground, but they can also be synthesized using high pressures and temperatures. So in the diamond now, we don't have two-dimensional layers, we have a three-dimensional structure. The atoms are bonded in all three directions to other carbon atoms. They're all held together by covalent bonds. The unit cell of the carbon is similar to the zinc blende structure. The unit cell here is limited by the geometry of the bonding orbitals. Diamond has a very high melting point, and it's very, very hard, and so it's really useful as an abrasive in a cutting tool because it also conducts heat away so that you're not melting the thing. Let's skip that one too. There are lots of other forms of carbon that are relatively new. Back in the 1980s, people messing around with lasers, shooting lasers at carbon surfaces, discovered what's commonly known as a buckyball. It's a whole category called Buckminster fullerenes. These are soccer ball-shaped clusters of 60 carbon atoms. It's really kind of crazy. Fullerenes, or buckyballs in general, can be from 36 carbon atoms up to over 100 carbon atoms. And then graphene is what we talked about at the very, very beginning. A single layer of carbon. So this is, right here, this is a graphene nano ribbon. So this is essentially one layer of graphite. It's one carbon atom thick, and it looks a lot like chicken wire. You can take that and make it into a tube. Those are called nanotubes. You can have a single-walled nanotube, or you can have multiple nanotubes nested inside of each other. And these nanotubes are very, very strong, but much less dense than steel. So the nanotubes are 100 times stronger than steel, and only 1/16 is dense. So that makes them very useful for things like bicycle frames, golf clubs, anything where you need strength with low density. These also conduct electricity, and so these can be, you can use bundles of these nanotubes to form really, really tiny wires. Lots of cool stuff being done with that. Another kind of network covalent atomic solid are silicates. Silicates are arrays of silicon and oxygen, so these are a little different because there's two different elements in here, but the elements are covalently bonded throughout the entire structure. Sand is predominantly different forms of silicate, and you know how much sand there is in the world, right? There's tons and tons of sand. Silicates make up about 90% of of the Earth. So silica has the formula unit of SiO2, but it's not a single molecule. That is the lowest ratio of silicon to oxygen atoms, and they are covalently bonded together throughout. So quartz is one form of silica, and there are many other forms. Ceramics, there are different types of ceramics, and I would encourage you to read about those.